Hello, I'm Bianmar Anderbongol, and this is my solo final project for data science and architecture. Um, I am alone in this project, so it will be quite low quality compared to the usual um, quality for other groups. I tend to be very bad at the types of this stuff, so let us begin. Let me just do the timer. So here's my data gathering. For this project, I followed the traditional method of obtaining data, which is then loading it directly from an online source. The dataset titled "Who Stole the Dogs Out" was sourced from Kaggle, a popular platform for data science competitions and open data sheets. I downloaded the zip file from the Kaggle page and extracted its contents. The primary dataset for analysis is MPMS stolen animals dashboard data November 2033 CSV. This file contains over 5,000 records of reported animal thefts across various London bureaus from January 2010 to November 2023. Each record includes details like type of animal, the bureau where the theft occurred, the type of offense, and whether the animal was eventually recovered. To enrich the analysis, I also gathered supplementary data from the same source. This includes bureau population, for demographic context, bureau's London CSV, for geographical and political information, and election CSV to explore potential correlations with local political control. All these files were uploaded directly into the Google Colab Sessions file environment for processing, as you can see over here, each one. So here's the first cell one, loading the data. This code loads our CSV files into the notebook so we can work with them. Here it is. Yep, filter, index to bureau. You can, Croydon, type of offenses. You can edit the info here. Like, for example, let me just cover it. As you can see, it's working, I think. 1 out of 5 entries, and just type of animal. Yeah, there's no dogs. One Easton, as you can see, animal recovery, many more. It works, but I'm not good at using stuff like this. Next is the data cleansing. Following the garbage in, garbage out principle, the next crucial step was to clean prepare the data for analysis. My process involved several key tasks. Handling inconsistencies, I started examining column names for consistency, renamed columns to have a uniform lowercase format with underscores, which is easier to work with in code. Data conversion, I noticed that the year and month column was stored as text. To perform time-based analysis, I converted it into a proper date-time format. I also checked other columns to ensure they had the correct data types, e.g. numbers as integers, text as strings. Checking for missing values, I systematically checked each dataset for missing or null values. In the main stolen animals dataset, I found a few rows of the missing information because these rows represent specific crimes. Simply deleting them might remove valuable data. Instead, I filled the missing type of animal with unknown to preserve the record. Going back up, here it is. And the filter. Where is it? Sorry. I'm a bit forgetful. Hold on. Unknown. Well, that works. That Standardize, and also going back, I also did de-standardizing and filtering. I standardized the text columns, like type of animal and bureau, to have consistent capitalization, which helps prevent dog and dog from being treated as different categories. Finally, I filtered the main data set to only include records from the year 2010 and onward, as the data before was sparse. Merging data sets. Feature engineering. To enable more insightful analysis, I merged stolen animals data with the bureau population data. This allowed me to create a new feature, thefts per capita. This new column represents the number of thefts relative to the population of each bureau, providing a fairer way to compare grammars across different areas. Here's the cleansing operation. There we go. Let me just theft, handling, robbery, dog. Not recovered. Okay, next is exploring data analysis. General problem statement. The Metropolitan Police Service MP5 wants to understand the patterns and characteristics of animal thefts. For this general problem, I formulated 3 specific data science questions to guide my explanation. Data science question 1, which type of animals are most frequently stolen? Has this trend changed over time? Data science question 2, which London bureaus have the highest rates of animal theft, especially when adjusted for population thefts per capita? And data science 3, what factors like animal type, bureau, or offense type seem to be most strongly correlated whether a stolen animal is eventually recovered? And here's number 3. Question 1. Most frequently stolen animals over time. And it is a dog, as you can see. It is the most easy to steal and, of course, the most readily found. Let me see. Alright, next. Bureaus with the highest theft rate per capita. Barking and Dagenham has the highest, as you can see, around nearly 700 theft per 1,000 people. It's a lot. And of course, factors influencing recovery. Recovery rate percent. Then this one is 40%. Now, X, cat, and dog. The dogs have the highest recovery rates, because while they are the most kidnapped, they are also the most common to be returned. To answer my third data science question about the factors influencing animal recovery, I built a predictive model to a feature extraction. I selected several features from the clean data set that I hypothesized would influence recovery. These features are animal type, bureau, offense set, that's for 100K in the month, year of the theft. The target variable, what you want to predict, is recovered. B is data preparation for modeling. Machine learning models cannot work with text directly. I use a technique called one-hot encoding to convert the categorical columns, animal type, bureau, offense type into numerical form. I also separated the data into features. The input variables are X and target the input we want to predict, or Y. Model training and testing. I split the entire data set into training set, 80% of the data, and in the testing set, 20% of the data. The model learns patterns from training data and then evaluated on unseen testing data to see how well it generalizes. For this task, I chose a decision 3 classifier because its results are relatively easy to interpret. Evaluation. After training the model, the final step was to evaluate its performance. Using test data set that it had never seen before, making predictions, I used the training model to predict the recovery status for animals in the test set. Interpreting the results to evaluate the model, I looked at more than just overall accuracy. I use precision recall and F1 score. These metrics are important, especially for imbalanced data sets like this one, where we have far fewer recovered cases than recovered. Precision. When model predicts an animal will be recovered, how often is it correct? Recall. Out of all the animals that were actually recovered, how many did our models correctly identify? Actionable insights. The model performance shows that predicting animal recovery based on these features alone is challenging. However, the EDA provided clearer insights. Target hotspots. Law enforcement should prioritize bureaus like Hounslow, Croydon, and Hillingdon, which have the highest theft rates per capita. Animal focus. While dogs are stolen most often, crimes involving birds and fish often involve large number of animals in a single incident. Have low recovery rates, suggesting a different kind of criminal activity, e.g. theft from pet shops or breeders. Recovery factors. The type of offense seems to matter. Animals stolen in theft and handling cases have different recovery profile than those stolen in burglary or robbery cases. This can inform how police investigate each type of crime. Here's the result. Precision is 0.92, 0.92, 0.92 for F1 score. Confusion matrix for recovery prediction. It is predicted, recovered, not recovered is 800. As you can see, this is okay, and that's the program. It's designed to help out for using the Kaggle Who Let the Dogs Out.